I guess you can hear me. All right. Hi, everyone. Thanks for being here to listen to the presentation of our work. So it's something about unconstrained submodular maximization in a stochastic bandit setting, and we propose an algorithm satisfying logarithmic regret upper bound. Okay, so let us present ourselves. I'm Julien. I'm a PhD student at Grenoble and at Inria. And by the way, I'm defending at the end of this year if you have a job. And it's a work that I've done with my incredible supervisors that nearly arrived late. Pierre, Gaillard, Thibaud, Rahier, and Julien Arbel who are there. Okay, now let's go to the subject. I'll talk about submodular optimization. I'm not sure you're all familiar with that, so I'll just begin with the basics. What's a submodular function? So it's a set function, so it takes as argument set, let's call it from a superset, let's call it G. A function is said to be submodular if when you add an item to a set, let's say A, the increase in value is bigger than if you add this item to a bigger set, which is B here. So that's what is a submodular function in mathematical definition. In concrete problems, this kind of behavior appear in several settings. For example, in your everyday life, in the restaurant menu, you often see that when you take the individual prices of items and you sum them, it's usually bigger than if you take them inside a combo. So that's a kind of submodular behavior. Afterwards, there are also some more industrial settings. Here on the right, you can see the mobile network coverage around Grenoble. You can see a lot of things, but actually, when you consider that problem, actually, when you add an antenna to this kind of network, the increase in value, so the increase in coverage, will be bigger if your set of antenna is smaller or sparser than if it's bigger. So that's also a submodular behavior. Okay. So our problem, the problem that we considered was unconstrained submodular maximization. So we have a submodular function that we try to maximize. It's a theoretical computer science problem that have been studied in the literature. There are some results. Notably, there's an impossibility result from 2011 saying that if you only have a sub-exponential number of cores, there are some instances where you can't have better than 1/2 of the best set. You can't find it in less than an exponential number of cores. And in 2012, there's Buchbinder, that proposed an algorithm satisfying this guarantee, this inequality. So it's an algorithm, double greedy, that finds a subset that is in expectation better than 1/2 of the best set. So there's an expectation because it's a randomized algorithm. So in the offline setting, we have these results. I'll delve a little longer into double greedy because our algorithm is based on it. So let's look at it and look at how it works. So it considers all the items in the sequential manner. It initializes two sets, x0 and y0. x0 is the empty set, y0 is the full set. So for the first item, it looks at the increase in value that you have for the x set when you add the first item. So it's the alpha 1. Alpha I here, and the increased value that you have if you remove the first item from y0. It will be beta 1 here. It's beta I. It makes a trade-off with the coefficient pi. After that, it samples a Bernoulli random variable and makes the decision to either add or remove the first item to x0 or from y0. and it goes on with the rest of the items. Here, in this example, it has decided to add the first item, remove the second, add the third one, and at the end, these x and y sets will converge towards the same set. And in the analysis, they proved that this set at the end is in expectation at least 1/2 of the best value. Okay, so we've seen that in the offline setting. So now let's go to an online setting and bandit settings. So now we consider big T rounds. At each round, there's a player that chooses a set 80. It receives reward that is the submodular, that is f of 80 plus a noise. So it's a noisy reward from a submodular function, and but we don't know f. And our objective would be to classically minimize an approximate pseudo rate. So pseudo rate is usual in stochastic settings, and there is a 1/2 approximation ratio from the 1/2 impossibility result earlier. It has been studied in the literature in both the stochastic and adversarial settings, and in both settings, algorithms have been proposed that satisfies T to the 2/3 upper bound. But as the stochastic settings intuitively may be more or less easier than the adversarial setting, the question that we had was, is it possible to get better upper bounds in the stochastic settings? And we actually propose a method that does, and that have logarithmic upper bounds. That's it, logarithmic upper bounds. Okay, so to find this kind of approach, we went back to the double greedy from the offline setting, and we looked for some sort of slackness into the analysis where we could gain some value. And so if we go back to double greedy, we look at the analysis, how does it work? It just takes this difference of 1/2 of the best value minus the last set. It upper bounds that with a sum of losses that corresponds to, so there's one loss per item that have as coefficients the weight of the algorithm, pi, and the alpha I, beta I, that were the marginal gains from the sets. And it uses the fact that this sum is smaller than 0, so this difference is smaller than 0, and at the end in expectation you have better than 1/2. So it uses the fact that it's smaller or equal than 0, but what we observed was the fact that this inequality could actually be strict. So there's some sort of slackness, and we could gain something from that. And in what we call easy instances, I develop a little further what we mean by that. We can have this inequality strictly smaller than 0, so f of xd being bigger than 1/2. So one may wonder if there's contradiction here with the 1/2 impossibility result, and there's actually not, because this impossibility result is really a worst case result. It tells you that for an algorithm that makes less than exponential number of calls, there is an instance for which you can't have better than 1/2, but actually instance per instance you can have better. So there's no contradiction, and we actually in our approach exploit this slackness that we have here. Okay, so the algorithm that we propose is an explore and commit type algorithms that is based on the double greedy from the offline settings. It begins with an exploration phase where it estimates coefficients alpha I and beta I that corresponds to marginal gains, margin gains from adding or removing items. It makes these estimations until a criterion is met. And at the end of this phase, it chooses appropriate weights pi. And after that exploration phase, it commits to a strategy where it continuously samples actions using these weights, and until the end of the T rounds. So what's new in these algorithms? There are two things. the stopping criterion from the exploration, because there are already been propositions of algorithms with this kind of strategy, but we propose a new stopping criterion that is kind of an early stopping that tells you that you have explored an item enough and you can stop, and I'll talk about it later. And what's new is also the sample strategy. Like instead of committing to a single set, we commit to a strategy where we continuously samples, and it allows us to have high probability results. Okay, so now let's go to the analysis of the algorithms. Here I have written the pseudo-regret. I can decompose this regret into what you lose in the exploration phase and what we have in the exploitation phase. What you find back here is the losses that we had before, the L, pi, alpha I, beta I, plus an additional term that is greater than 0 and that corresponds to high probability bounds for both the estimations and the sampling strategy. And as we have seen before that these losses can be strictly negative. So actually, if we manage to find a pi so that the right term is strictly negative, we can only pay the exploration. And if this exploration is, let's say, logarithmic in the number of rounds, we have what we wanted. And when it's okay, I'm at the end. Anyway, so okay, so what we wanted to do was to have the right term negative and to only pay the exploration. And to that, we still need to characterize what's the number of rounds for the exploration. We converge to these things that is kind of barbaric, but it's actually the inverse. It looks like the inverse of the suboptimality gaps squared in stochastic in classic Multi-arm bandit settings. At the denominator, you have the difference between alpha I and beta I. So what you gain between when you have to choose if you add or remove the items. So it just tells you that if those coefficients are very close, your decision, you will have to sample a lot to make a decision, while if they are far away, you can know pretty fast that you have to remove or add this item, and that's what you see here with the number of sampling rounds increasing in the first bisectors. So using this thing that we call the hardness, we have a mean of these two things for the upper bounds. We have the mean of a logarithmic term and a t to the 2/3, and that's what we have. And we also made some simulations, but we don't really have time. So come see our poster, and I can comment on them. Thanks. Yeah.
Modular bandit problem would be like a linear one?
Yep, it is.
And does this notion of hardness like capture that?
Yep.
In an intuitive way? Or?
Yeah, intuitively, it's just the number of rounds to see if, like, for a linear case, that's actually what we see here. It just see if, for your item, if it's positive or negative. So it's the hardness is, I removed it, it's 1/squared of your norm. So you just have to, with high probability, estimate if it's bigger or smaller than 0, and if it takes the decision, it stops. That's it.
And can you evaluate this HF for like a linear function?
Yep, it's the sum of 1/squared of, like, it's for here, it's 1/squared ti. Yeah, that's it.
L?
Oh yeah. Yep. No. Didn't write it here. So it's the max of two linear functions. So the first linear function is what you lose if you remove the item while it is in the best set and the other one is the opposite. So that's why it has this shape. And we look at the minimal of this thing, which is the PI.
Right, so the alpha and the beta are the slopes.
Yep.
And the P is the...
Yep. That's it.